Welcome guys. This lecture we shall discuss the group 6 elements of the periodic table. And now group 6 tells us we're talking about group 6A of the periodic table, not the B group of the periodic table, right? Alright, so what are group 6 elements? Group 6 elements are elements which have 6 valence electrons. Alright, and then either you call them the group 6 elements or you call them the oxygen family. They're called oxygen family because oxygen is the first member of the group of the family, right? And then if you do not call them the oxygen family, you can as well call them the chalcogens. Chalcogens means they are ore formers. So you call them oxygen family or you call them the chalcogens, meaning ore formers. And why are they called chalcogens? Because virtually every ore, every chemical ore you find in chemistry has at least one group 6 element. And now you can give examples of ores and you can see that at least there is a group 6 element present. For example, any ore of group 1 element, yes, sodium, or okay, let's see the common ores we have. We have cassiterite, we have bauxite, we have zinc blende, you have galena, you have hematite, you have any ore, right? You stand a 90% chance of finding a group 6 element. So what is cassiterite? Cassiterite is an ore of iron, right? It's an ore of tin, sorry. Cassiterite is an ore of tin and can be simply written as this. Oxygen is a group 6 element. That's why they are called chalcogens. They are ore formers. Bauxite is an ore of aluminium. Oxygen is a group 6 element. Zinc blende is an ore of zinc. Sulfur is a group 6 element. Galena is an ore of lead. Sulfur is a group 6 element. Hematite is an ore of iron. Oxygen is a group 6 element. So group 6 elements are called chalcogens because you find them in ores. And ores are naturally occurring forms of reactive metals, of highly reactive metals, and even non-metals. When you have highly reactive chemicals or highly reactive species, and they are put in the earth crust, they don't remain there alone because they are reactive. So they find other elements in the earth crust they can combine with, all right? And then when they combine with those elements, they form ores. So those ores are what you mine, are what you extract from the earth crust, right? So ores are naturally occurring forms of reactive species, and you stand a good chance of finding group 6 elements in most chemical ores, and that's why they're called chalcogens. Now, why are they called oxygen family? We stated earlier that they are called oxygen family because oxygen is the first member of the group. What other members of group 6 do we have? In group 6, we have oxygen, symbolized as O. We have sulfur, symbolized as S. We have selenium, symbolized as Se. We have tellurium, symbolized as Te. And we have polonium, symbolized as Po. So these are group 6 elements: oxygen, sulfur, selenium, tellurium, and polonium, right? And because oxygen happens to be the first one of the 5 of them, then you can also call them the oxygen family. So properties of chalcogens. Properties of chalcogens. Let's start with their physical property, then move to chemical. Okay, I just thought of combining both of them here. Now, the first thing is oxygen, being the first member, is gaseous. This is a physical property now. Oxygen being the first member is gaseous at room temperature. At room temperature. But other members of this group are solids. So oxygen is gaseous at room temperature, but at room temperature, other members are solids. That's number one. Number 2, right? Oxygen and sulfur. Oxygen and sulfur are non-metallic. They are non-metallic, right? Selenium and tellurium. Selenium and tellurium are metalloids, right? While polonium is metallic, is a metal. That's another physical property, right? So that's it. Now what about their chemical properties? They are found present in ores, right? Hence their name chalcogens. Hence their name chalcogens. That's another important point or property. Okay? Now, how many outermost electrons do you think they'll have? Since they are group 6 elements, it means they have 6 valence electrons, right? So they have 6 valence electrons, and that's why they are put into group 6 of the periodic table. And then what about their block? They are p block elements. They are p block elements. Look at this. Oxygen has an atomic number of 8, and sulfur has an atomic number of 16. Taking the configuration of oxygen, you have this 1s2, 2s2, 2p4, right? While for sulfur is 1s2, 2s2, 2p6, 3s2, and 3p4. Which is that? Makes sense. Now, what group does oxygen belong here? Because this has principal of 2, right? It means you add up their indices, 2 plus 4, and it gives you 6. So they belong to group 6 of the periodic table. Same thing happens to sulfur. The maximum principal quantum number is 3. So what are the indices of these 3? You have 2 and 4. 2 plus 4 also gives you 6. But what block do they belong? What is the final orbital they have their last electrons, or their outermost electrons? It's the p orbital. So it makes them p block elements, right? So that's another property, that they contain 6 valence electrons and are p block elements. What other points that we said about group 6 elements? They show allotropy. They show allotropy, right? So they are allotropes of oxygen and even isotopy, all right, as the case may be, allotropes and isotopes. Now, what allotropes do we have here? In sulfur, for example, right, there are 2 allotropes of sulfur, which is the crystalline sulfur and non-crystalline sulfur, right? Those are the 2 allotropes. Now, the crystalline sulfur, you have the rhombic and monoclinic sulfur. So, allotropes of sulfur here you have, let's do that here. You have sulfur, you have crystalline and non-crystalline sulfur. What are the crystalline allotropes of sulfur? You have rhombic sulfur, which is the most stable form, and then you have monoclinic sulfur, right? What about the non-crystalline form? You have plastic sulfur as the monoclinic sulfur, as you can see. So all these are allotropes of carbon. Allotropes, by the way, are different forms of a particular element, all right, the same chemical states but different physical appearances. So you have different physical appearances of the same elements, but they have the same chemical behavior, and that's why you call allotropes. And then this is then you, of course, you know sulfur industrially is prepared by Frasch process. Okay, we've talked about that in our lecture on sulfur and its compound. Oxygen is produced from fractional distillation of liquid air or liquefied air, all right, which also is an industrial way of producing oxygen. All right, so guys, that's it. And what else do we say about this group? What about their reducing abilities? What can we say about their reducing abilities or oxidizing ability, as the case may be? Now, group 6 elements are better oxidizers. The better oxidizers, or you say oxidizing agents, than group 5, right? The better oxidizers than group 5, but less as good as group 7. But less as good as group 7. What this means is, now oxygen has 6 valence electrons, right? Just as the rest others. And to these 6 valence electrons, it is easier for oxygen to accept 2 electrons than any member of group 5 to accept 3, right? So the fact that oxygen accepts 2 electrons more easily than group 5 makes them better reducing agents, or easier reducing agents to come by than group 5, right? So that's what we mean here, that they are better oxidizers than group 5, but they are less as good as group 7. Okay, and then of course we also need to state here that these elements prefer ionic or covalent type of bonding. Ionic or covalent types of bonding. That's when you find group 6 in their compounds, that it's either the most likely covalent or ionic. So guys, that's about group 6 elements. Now, but it's important to note that group 6 elements are chalcogens, which means they are all formers. It's also important to note that they are also called oxygen family, because oxygen is the first member of the group, right? These members, out of these members, oxygen is gaseous, while the rest of them are solids. Okay, oxygen, just like the rest of them, has 6 valence electrons. They show allotropy. They are good oxidizing agents, at least better than group 5, but less as good as group 7, right? And then they show, like we said, allotropy and several other points. So, and it is important to note that to biological life, oxygen is highly important because it is the major gas to be inhaled by animals, right? And one major source of oxygen inhaled by animals is given off by plants as a byproduct of photosynthesis. And then, so plants give off oxygen during photosynthesis, which we animals utilize, all right, for metabolic processes. Oxygen also comprises just 21% of the atmosphere, which makes it the second most abundant gas in the atmosphere after nitrogen, which is 78%, right? So these guys are very important. Oxygen is a major constituent of water, which we use in our everyday lives, all right? And then it just shows us how important this family is. Now, when you look at these elements one by one, that means when you look at oxygen and its compounds, sulfur and its compound and the likes, you look at how these guys can be prepared. We also look at the importance or the uses of these guys. But for this lecture, what we just do is we study their chemistry, leaving out their uses and their preparation. All we just want to know is why do they belong to that group and what are some of their chemical properties, which we've done. So thank you for sticking with us in this lecture. In the next lecture, we'll move to group 7 elements, one of the most important groups of the periodic table. Group 1, group 7, group 0. So please join us when we discuss group 7 of the periodic table and let's study their chemistry.